Yes, you can start. Thank you.
Okay, thank you. Sorry for the technical difficulties. So I would like to start by thanking to the organizers for organizing this and for inviting me. I will talk about entanglement and objectivity and pure dephasing models. So pure dephasing is what, as I see, you call pure decoherence. This was a work done together with Jarek Korbic, who is here, and perhaps of relevant information, perhaps not. I've changed jobs, so now I work at Palacky University in the Czech Republic. And I can actually change slides. So the talk is organized as follows. I will start with an introduction, which will be very short, which is probably good because the two talks before did a better job of that. I will say a couple of words about the idea of objectivity and then show the mathematical realization of this idea that I'm going to be investigating, which is spectrum broadcast states. Then I will talk for a bit about pure dephasing evolution, so pure decoherence, and how we can look at entanglement of a system with an environment in this, and then use this to say when these kind of SBS states are possible and or not. And then I will show what if we want really good SBS states, what does this mean for the initial state of the environment that we need to have, so for its purity, and for the entanglement which needs to be generated between the system and the environment. And then I will slightly change the topics. I will show you for the same kind of Hamiltonian how we can get SBS states, at least glimpse SBS states, for a completely different set of parameters without entanglement. You'll see it's weird that it's the same interaction, but it's completely different. So as an introduction, well, being at this conference, you all know what objectivity is, but I'm going to read this nice sentence because the formula which is below is exactly the realization of the sentence. So objectivity is the idea that classicality should emerge naturally out of the quantum description to allow unrelated observations of a system by different parties, which would neither destroy the state of the observed system nor leave ambiguity in the information obtained about this state. And then spectrum broadcast structure states, or SBS states, which come up in this work by Jarek, Paweł Hrodecki and Ryszard Hrodecki, are the exact mathematical realization of the sentence which is written above. So if a state has such a structure, we have, yeah, unfortunately, I have no mouse because it's a tablet, sorry. So we have a system that we want to learn the information about, and this is written in a pointer basis I. And this system is with a certain probability in pi in pointer states I. So for multiple parties to be able to learn about this system, we have the special product structure for each pointer state that the environment, if the pointer state is in state I, then environment K is in an appropriate state, rho I K. And so if there are measurements on the case environment, this does not change on average the structure of the state of the central system. You can just reconstruct it. But what is more important at least what will be more important for me, is this bit where you're supposed to learn about the central system state by measurement of the environment. And this requires these states of the environment, which are conditional on the pointer state of the system, to be mutually orthogonal. So these are density matrices, but this condition on the right is exactly the mixed state counterpart to having two states which are orthogonal to each other. So, and now what I'm going to study is some kind of more or less realistically modeled evolution, pure dephasing, as mentioned before. So the question is, what are the requirements for such a state to emerge during this evolution? And there are actually two. One is that we need decoherence. Obviously, the pointer states here are those are projectors. There are no off-diagonal elements in the system subspace. So we need some source of decoherence, which we will get by an interaction with an unobserved environment that reduces these off-diagonal elements to zero. And the other thing that we need is the interaction with the observed environments K, so that we have this structure that every pointer state has a counterpart in the environmental states, and then these are mutually orthogonal. Okay. So now I'm going to be studying pure decoherence, pure dephasing evolutions. And usually when I do this, I have to justify why I only study pure dephasing, which is probably not very necessary here, since for the study of Darwinism and objectivity, pure dephasing is very natural, but I still will very shortly. For one, it's the dominating mechanism for solid state qubits, like the NV centers mentioned before. It's a good choice for objectivity, because there is a chosen pointer basis in the system of interest, and this is naturally chosen by the interaction. So there's no ambiguity here. And the actual reason why I study a lot of pure dephasing is that to a surprisingly high extent, these types of Hamiltonians can be analyzed on a general level. There's very strong ways of studying this system, such systems and environments. So below I have a Hamiltonian, and this Hamiltonian, you can see on the right, we have a sum over all the pointer bases of the system. The first term is the free evolution of the system. Then we have the interaction with the unobserved environment, and then we have all of the interactions with the observed environments. So this is pure dephasing, which means that if we trace out all of the environments, the only thing which can happen is that if you have a density matrix of your system written in the pointer basis, then during the evolution, only the off-diagonal elements of this density matrix will be affected. A side note in this Hamiltonian, I also have the free evolution of the environments. It's just hidden in the interaction terms. And the condition for it to be pure dephasing is that this free Hamiltonian of the qubit has to commute with the interaction part, which is obviously fulfilled here. So if we have this special form of the Hamiltonian, we can find a simplified general form of the evolution operator, which is written below. This is because the pointer basis of the qubit does not evolve with time. And again, this evolution operator has a nice structure with sort of conditionality implied. So what it means is that if the system is in pointer state I, the environments will evolve according to this thing that stands on the right. I'm going to make one more assumption here about the initial state, and this is a pretty strong assumption. I'm going to assume that there are no correlations, no initial correlations between the system and any of its environments, and that there are no initial correlations between the environments either. So it's a product state. No classical or quantum correlations. Another assumption that I make here is that in the initial state of the system is pure. And this assumption is actually relevant because if the initial state of the system is pure, I can say things about the entanglement with the environment. And if I have mixed states initially, then it becomes a mess, and then I have to treat everything on a specific basis. So I can't draw general conclusions yet. Okay, once we have this, we can find at least the formal form of the density matrix at any time t. It is written down here for a qubit, can be easily generalized, and the way this is written is it's in matrix forms with respect to the qubit pointer states in the pointer state basis. So this is actually a really big matrix. Just you can see this really pretty and convenient structure that each quarter sort of has a different separate matrix that that describes the system environment state conditional on the pointer state of the qubit for the diagonal parts and the correlations within for the off-diagonal parts. Okay, so so what these matrices of the environment are depends on, well, where this matrix was, where the environmental matrix is, but if the evolution is given by those conditional evolution operators on the environment. So this is it's reasonable to okay, it's fairly easy to deal with this because the structure is so organized, so to speak. So we want SBS states. So the obvious next step is tracing out the unobserved environment. And after doing this, we still get a pretty big matrix, which is written here below. Again, in matrix form with respect to the qubit pointer states. And now, instead of the density matrix of the unobserved environment, we have a decoherence factor. And for SBS states, we need this decoherence factor to be equal to 0. Now, I'm not going to worry about this bit particularly because, at least as we have in solid state qubit, obtaining full decoherence, I mean complete decoherence, is reasonably easy, happens very naturally as long as you have a bigger environment with a somewhat random structure of its energy distribution. If it's big enough, then after you wait a bit, you will get this full decoherence, and this simply happens naturally, even though we would very much like it not to. So this decoherence, at least in case of solid state qubit, is usually very easy to obtain, pretty hard to get rid of, and it's a natural assumption that this will happen. So what I am going to focus on, this here we have this matrix, the system observed environment matrix, when this unobserved environment caused full decoherence. And what I'm going to focus on is how does what conditions I need to have on my interaction, on my joint evolution of the system and observed environment to have perfect distinguishability of the case environment. So my experimentalist wants to be able to measure his environment and learn exactly what the probabilities pi are. For this, he would need the states, his environmental states, to have mutually orthogonal supports. And the most, at least convenient for me, way of writing this is that his two, in case of the qubit, density matrices, well, yeah, they are density matrices, multiplied by each other gives 0. If this would be fulfilled, he would have he would be able to gain full information about the qubit state by measuring the environment. Okay, but this is a pretty strong condition. It's even a very strong condition. I will show you the consequences of this in a moment. So let's make this much weaker for just a second. So let's say that the experimentalist has a lot of tolerance, and he does not need to gain the full information, but he wants to get any information at all. So to get any information at all, these two states do not have to be orthogonal to each other. It's enough that they are not the same. So the question is, does this translate to any properties of the full density matrix? So the one that has the unobserved environment as well. And the answer is yes. For this to be fulfilled, for the two states not to be the same, there has to be entanglement between the qubit and the observed environment. So perhaps I should note that I'm dealing with mixed environments for the most part. I mean, the pure environments are just a special case, and it's mixed environments, so like thermal equilibrium environments, that I'm interested in. So here again, we have the qubit environment density matrix for all environments, including the unobserved one. And for this type of density matrix, there is a reasonably simple separable if and only if separability criterion, and this full separability criterion is written below. It just says that the density matrix of all of the environments conditional on the qubit in being in state 0 has to be the same as the density matrix of all of these environments conditional on the qubit being in state 1. So if there is no qubit environment entanglement, the separability criterion is fulfilled, then for all observed environments, we still have decoherence. This does not say for mixed states, you can have the decoherence without entanglement generation, and you very often do. But yeah, so if we have no entanglement with the environment, then the conditional density matrices of each environment are the same. So there will be no information about the qubit that can be gained by measuring the environment in the absence of qubit environment entanglement. And so we can relate pretty simply that entanglement, which is a definitely quantum property, is a necessary but not sufficient condition for objectivity, which is the emergence of a very classical state. Okay, so this is the smallest, the weakest condition that we get, and we already know that to even talk about this transfer of information, we need to have an entangling interaction with the environment. But let's look at the other sides. Let's look at the situation where we want to have full information about the qubit state in the environment. So we referred to this as strict distinguishability, and the question is, what does this condition imply? So it actually has two pretty strong consequences. The first one, at least, was surprising for me. So it turns out that if your environment is supposed to get the full information about your qubit state, there is a limitation for the initial purity of the environment from the bottom. So you have to have some purity in your environment. It can't be the minimum purity for this condition to be fulfilled. So this works like this, that you can write the conditional density matrix of environment K in its diagonal basis, and then you can write the other conditional density matrix in its diagonal basis, and if string distinguishability is fulfilled, these two bases have to be orthogonal to each other, meaning that each state n has to be orthogonal to each state n perpendicular. So this means that only together, since each state in one basis is orthogonal to each state in the other basis, only together they form the full eigenbasis of the environment. And if you note the way that these conditional density matrices of the environment look, they have the same number, they have the same coefficients. They are a mixture with the same probabilities. So the number of non-zero coefficients, of the number of relevant states in each of these diagonal bases, is the same. And now if you take it together with the fact that the purity of the initial state of environment K has to be the same as the purity of these conditional states, because they are obtained by unitary evolution, then it will turn out that the initial purity of environment K has to be at least twice as big as the minimum purity for an environment of a given size. So this, this means that you will only have strict distinguishability, so the real SBS structure, SBS states, if your environment is initially at least somewhat pure. It can't be very mixed. This strongly depends on the size of the environment. I mean, what this means strongly depends on the size of the environment, in the sense that if your environment is a qubit, this means that your initial state must be pure. But if your environment is big, it can still be a reasonably mixed state, just not maximally mixed. But, okay, and the second consequence is for qubit environment entanglement. Just checking how's my time. For qubit environment entanglement, if we look again at the full density matrix with with everything, with the unobserved environment as well, you can not only write the density matrices of the observed environment in their diagonal bases, but you can also write the off-diagonal elements in the diagonal basis. So The difference here is that the bases n and perpendicular have to be composed of mutually orthogonal state, while for the unobserved environment, it doesn't matter. This can be the same basis. It can be slightly different. But since entanglement, it doesn't matter whether your decoherence comes from entanglement or not. This on the right side can be anything, but you can still do the trick. So if actually the density matrix here is written for one environment, but this is easily generalized to many and to as many environments as you want. It would just be more talking, and I'm already pressed for time. So if you do this, you can use these bases to write a pure state decomposition of your density matrix. And the pure states here are these nice bell-like entangled states where you get maximum entanglement for a given qubit occupations. But the relevant thing to note here is that these states occupy different subspaces of the environment. So if you change this pure state decomposition into any other pure state decomposition, it will also be composed only of states with the same amount of entanglement. So it's nice because you can calculate the amount of entanglement you need. But the bad thing is that these are states with the maximum entanglement for a given qubit occupation. So the thing we learn here is that distinguishability really requires a lot of entanglement. So what we get here is that on the one hand, you need entanglement to be able to distinguish by measurement of the environment what your qubit state is at all. If you want to have the full information, you need to have as much entanglement as possible. And hopefully there are all those possible situations in between when you get only some information, and perhaps this can be somehow remedied by you can learn more information by taking more environments to one observer and so on. But nevertheless, these are very stringent conditions, which is kind of bad. Okay, and so to end on a positive note, or more in the realm of fun facts, there's actually a completely different ways to get SBS states still having pure dephasing evolutions, but a situation which requires no unobserved environment, so we don't require a decoherence source. And also, we will be studying the situation where the evolution is separable, so no qubit environment entanglement. And so, yeah, we call this a glimpse of objectivity because this can happen only at distinct point of times, but nevertheless, it's interesting to see because it's so completely different in almost every possible way from what I was talking about before, but nevertheless, you get the same SBS spectrum broadcast structure. Yeah, so let's look at a qubit with a single environment. As I said, no unobserved environment, and we have still pure dephasing, but the condition of separability is fulfilled, which more or less translates to the fact that you can diagonalize the conditional density matrices of the environment in the same basis, meaning they commute, so they're yeah. Sorry, so you can diagonalize the density matrices of the environment in the same basis as this conditional evolution operator of the environment. So if you have this separability condition, you are again able to decompose your density matrix into pure states, but this decomposition looks completely different because it's obviously separable. It's even it has zero discord with respect to the environment. And so this means that automatically the states of the environment are mutually orthogonal and they're pure. So in this case, the problem is not the environment. You can learn all you want from the environment because we have a pure basis of states for the environment, but the problem are the states of the qubit, because the states of the system actually. Oh no, I said it was a qubit. So the problem are the states of the qubit where you well, they evolve and they will only be orthogonal to each other from time to time. So let's quickly look at an example. The example is the simplest one possible. We only have a single qubit which forms our environment, and then for this state at the bottom here to have to be an SPS state, we have one requirement, that is that we need an equal superposition initial state of the qubit, and then it will be enough to wait long enough until psi0 state and psi1 state are orthogonal to each other. So obviously I have a mistake here. This product should be 0. Yeah, so it's reasonably easy just by waiting with no other, with no decoherence mechanism, no system environment entanglement formed. You simply have to wait, and periodically the SBS states will emerge. Obviously, two qubits, so a qubit system and a qubit environment, are the easiest situation to obtain this, but it can definitely be generalized to larger environments. You can observe this for larger environments. You can observe this for larger systems, but this kind of situation will not emerge for more environments. And yeah, so the structure only appears at instances of time. And the sort of interesting thing to note here is that the basis in which you have this, the qubit basis in which you have this SBS structure, is as different from the pointer basis we had before as possible. One are equal superposition states, and the other one were pointer states. Okay, and this is it. So the conclusion is that for the first part, entanglement is irrelevant for decoherence necessary to obtain these structures, spectrum broadcast structures, but it is a necessary condition for distinguishability of system states by measurement on an environment. If you want to learn everything, so strict distinguishability, you will need the environment to initially contain a certain level of purity, twice the minimum, and it also requires you to have the maximum possible amount of entanglement in a given state, which can be problematic. And we have generally shown that the requirements for SBS are stringent. But on the other hand, we've also shown that this is not the only way to obtain SBS states, and yeah, they may emerge in less straightforward ways during some joint system environment evolution. Thank you.
Thank you so much, Katarzyna, for your talk. Basically on time, we have some time for questions now. Does anyone have questions? Okay. If no one has any questions, let me just ask something quickly. Have you ever tried it without dephasing models? Like if you have a non-pure dephasing model, do you still need entanglement?
Again, with you mean other types of interactions?
Yeah, other types.
The answer is yes, but I mean, I have tried, but this is so the nice thing about pure dephasing is that it chooses your pointer basis. And once you have a pointer basis, you know sort of what you are looking for. When you have different type of interactions, so you don't have the pointer basis, and what you get in general is a mess. And once you have pure environments, it's deciding what is the optimum basis, you know, to have your SBS state. The problem is that the optimal basis for looking at this SBS structure is changes with time. And on the other hand, you still need some kind of decoherence source, and you want the decoherence to come to zero. So the answer is that I did look at it, but outside of pure states of the environment, it's really hard to get any sort of conclusion. I mean, we would probably have to look at mutual information the way that the previous speaker did, because then you don't have to really answer the question, what is the experimentalist supposed to measure on the environment? And once he has the measurement outcome, what does he learn exactly? Because this gets really fuzzy.
Okay, thank you. I guess that makes sense. It just becomes more and more complicated. So
but it becomes complicated to the level where it's really hard to ask a meaningful question.
Okay, we actually, if your comment is short enough, or else we should move to the next speaker. Yeah. Did you want to just say something quickly while?
No, I just wanted to comment that when you in the more general interaction situation, it's even difficult to say what is decoherence when you don't have a clear pointer states. There are some ideas by Wojtek Żurek, for example, but in general, this question is like difficult already at the fundamental level to say what is decoherence, not to mention building up on that, like Darwinism and related concepts.
Okay, great. So thank you, Jarek. Thank you, Katarzyna.